Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Hello, everyone, and welcome. This is week 10, part 1, and today we are doing a deep dive into the foundations of diffusion models. We're going to break this whole thing down from first principles, really get to the core of how these incredible models learn to create such amazing images from, well, nothing but pure noise. Let's get right into it. So here's our game plan. We'll start with the big picture, kind of see where these models fit into the whole AI universe. Then we'll hit the main intuition, this idea of destruction and reconstruction, before we really get into the nitty-gritty of the forward and reverse processes. After that, we'll see how the model actually learns, and then we'll tie it all together with a nice summary. All right, first things first, let's get some context. Before we can really appreciate what makes diffusion models so special, we got to understand the neighborhood they grew up in. Okay, so this map here lays out the main families of generative models. On one side, you've got your explicit density models, things like VAEs. They're pretty stable, but, their results can be a little blurry. On the other side, you have implicit density models like GANs, famous for those super sharp images, but notoriously unstable and tricky to train. And then, right in the middle, you see diffusion models. They kind of thread the needle, creating this powerful hybrid that takes the stability from one side and combines it with this incredible high-quality generation process. This chart gets at what we call the generative trilemma. The basic idea is you have to juggle three things: the quality of your images, the diversity of what you can create, and how fast you can do it. And usually, you can't have all three. See, GANs give you amazing quality, but they can get stuck in a rut, lacking diversity. VAEs are super fast and diverse, but the quality isn't always top-notch. But now, look at that thick teal line for diffusion. It pretty much maxes out both quality and diversity. So, what's the catch? Speed. That step-by-step creation process is incredibly powerful, but it definitely takes its time. Okay, now we're getting to the absolute heart of it. Seriously, if you remember just one thing from this entire explainer, make it this next concept. It's the key to everything. So here it is, the big analogy. Imagine you drop a single perfect droplet of ink into a glass of water. It spreads out, gets chaotic, and the information, that perfect drop, is lost. That is the forward process. It's easy. It's predictable. It just happens. Now, what if I asked you to reverse it? To reach in and pull every single ink molecule back into that one perfect droplet? That seems impossible, right? That is the reverse process. And that impossible task is exactly what a diffusion model learns to do. It learns how to undo chaos. Okay, so let's get into the mechanics of this. Starting with the easy part, how do we systematically and controllably destroy an image? This process isn't just random splashing, it's a very controlled demolition. It's a Markov chain, which is just a fancy way of saying that each step only depends on the one right before it. No long-term memory. And at every single step, we add a tiny bit of noise. How much noise? Well, that's determined by a variance schedule. It's basically just a pre-planned recipe. And what kind of noise? Always the simplest kind you can imagine, standard Gaussian noise. That's it. A simple, repeatable process for turning any image into television static. Now, adding noise one step at a time would be super slow, but thankfully, there is this beautiful mathematical shortcut. It turns out, because of how Gaussian noise works, we don't have to walk the whole chain. We can use this one equation to just jump directly to any point in time, t. We give it our starting image, tell it how far to go, and poof. It gives us the correctly noised-up version instantly. This is a massive, massive efficiency win when we're training the model. So, why does all this matter? What's the point? Well, look at the geometry of it. Our original data, all the images of cats or whatever, might exist on some incredibly complex, twisted shape in high-dimensional space. But as we keep adding noise, that complex shape gets smoothed out, and eventually it just becomes a simple, predictable sphere, a standard Gaussian distribution. And this is so critical because it means that no matter how complex our image was to begin with, the end state is always the same simple known thing. We have a predictable starting line for the reverse process. And now, for the magic. We figured out how to systematically destroy an image. How on earth do we teach a computer to reverse that process and create something from the static? Here's the problem. The true reverse step, that complex red curve you see, is what we call intractable. To figure it out perfectly, you'd basically need to know about every single possible image in your dataset. It's just impossible. So we cheat. We use a neural network to learn a simple approximation, that friendly blue Gaussian curve. The entire goal of training this model is just to get our simple, learned blue curve to be as close a match as possible to that impossibly complex red one. And the tool for this job is a special kind of neural network called a U-net. Its job is actually pretty straightforward. It takes in two things: a noisy image and the current time step t, so it knows just how noisy the image is. And its goal is to predict the mean, or the center of that blue Gaussian we just talked about. The spread, or variance, is usually fixed, so the network really only has one job: predict the center of the target. And that center just so happens to be the denoised image one step back in time. Okay, so we know the network has to predict the previous step. But how do we actually teach it to do that? What's the homework assignment? What's the loss function it's trying to optimize? Now, you might be thinking the obvious answer is to just have the network predict the less noisy image directly. And that makes a lot of sense. But it turns out there's a much, much smarter way to set this up. A really critical insight is about to drop. The model doesn't predict the image. It predicts the noise. And this right here is a huge aha moment. Instead of making the network guess the clean image, which could be a bit ambiguous, we give it a much simpler, more concrete task: just predict the exact random noise that we added in the first place. This little change, this reparameterization, makes the learning target so much more specific and stable, and that leads to way better results. It's a real game changer. So why is predicting noise so darn powerful? Well, it's because it's basically the same thing as learning something called the score function. Look at this visual here. The model is learning the direction of all those tiny arrows at every single point in space. Those arrows are like a map that tells you, hey, if you're a random point out here in the void, you need to move in this direction to become more like a real image. It's learning the underlying structure of the data itself. So stepping back for a second, what's the big mathematical goal here? Well, ideally, we want to maximize the likelihood of our training data. But that's just computationally impossible to calculate directly. So we use this clever proxy called the evidence lower bound, or ELBO. Think of it like this. The true likelihood is a ceiling we can't touch. The ELBO is a floor right beneath it. We can't push the ceiling up, but we can push the floor up, and by doing that, we force the ceiling to rise along with it. It's a really smart workaround. Now, when you unpack that ELBO math, you find it's made of a few different pieces. A couple of them are pretty much constants or easy to handle. The real action, the part where all the learning actually happens, is in that big red box on the slide, the denoising term. This is the piece of the equation that mathematically forces our model's guess for the reverse step to match the true reverse step one time step at a time. And here it is, the beautiful payoff. After all that theory, Markov chains, intractable posteriors, ELBOs, KL divergence, it all comes crashing down to something ridiculously simple. It just so happens that measuring the difference between two simple Gaussian curves is the same thing as measuring the squared distance between their centers. And this simplifies our entire complex objective function into a basic mean squared error. And the interpretation of that final simple math is just perfect. At the end of the day, to train a diffusion model, we simply take an image, add random noise, and train the network to guess what noise we added. That's it. That's the entire training process in one sentence. All that complexity for such an elegant, simple idea. All right, let's wrap this up. Let's put all the pieces back together and look at the complete algorithm from start to finish. And here you have it, the whole shebang on one slide. On the left is the concept, right? A fixed forward process adds noise. A learned reverse process takes it away. And we train it by just having it predict that noise. And on the right, you see how that concept becomes a real algorithm. It's just a simple loop. Grab an image, pick a random time to jump to, add the right amount of noise, and then you ask the network, hey, what noise did I just add? That's it. You just do that over and over again. So we now understand the what and the why of diffusion models, right from the ground up. But this leaves us with some really interesting new questions. We mentioned that U-net architecture, but what makes it so good for predicting noise? And maybe more importantly, once we have this amazing denoising machine, how do we actually guide it to generate a specific thing, like a photorealistic painting of an astronaut riding a horse? Well, that's exactly what we're going to dive into in part 2. Thanks for tuning in.